feel like class is starting, and then you'll just be beating me up on the ground.
People at home, we collected the worksheet from yesterday. Don't forget JLab is due tomorrow, and we talked about the SOL test. You'll catch up later. All right, here we go. All right, so we're talking about gases. JLab number 2, due by start of class tomorrow. Don't forget. You may have other written homework. Maybe we'll get to that later. Whatever. Maybe, maybe not. Okay, here we go. You're going to need your calculators for sure. Those need to be handy because we're going to be talking about and doing math. Okay? None of this math is hard, I don't think. What is somewhat problematic sometimes is remembering the equations on the SOL test. But there's 2 that you need to know for sure. One of which is like an equation, but it's even not really. It's super, super easy. I'll show you that one. But then there's one gas law equation that you super, super have to know because it's always on there. Okay? All right, so we're talking about gases. Okay? Gases have mass and they occupy space. Typically, gases are lighter, meaning they don't have as much mass as other substances because they are less dense. Okay, remember density is a combination of mass per unit of volume. So their mass is relatively low compared to their volume. But they do have mass, they do take up space. Now, there is a relatively large amount of space between gas particles. This much is review for you. Now, it's been a while since we talked about this. We need to jog our memory. Kinetic theory of matter. Don't talk. Popsicle stick. Testerman. Kinetic theory of matter. What is it? No. You ain't got time to look it up. Flesh it out with me. What is it based on its name? Okay, what's kinetic energy? It's energy of motion. So the kinetic part is motion. So the kinetic theory of matter is the theory that matter is in constant motion. Yes?
Yeah.
Do we remember this? Yes? You're like, what? We learned that? Totally. My fists. Barely moving. Who is this?
Solid.
Solid. But are they moving?
Yes.
Yes, because all atoms are in constant rapid motion according to the kinetic theory of matter. Solids. Barely moving but moving. Yes? Slip slide over each other. Who's this?
Liquid.
Liquid. And we can pour them. Yes? Super far apart relative to solids and liquids we have gases, lots of space between them. Now, it's not the space between here and Fort Chiswell space, okay? But it is the space, they're almost touching in solids. There's enough space that they can do slipping and sliding in liquids, and then there's several lengths of atoms, if you will, space between gases. Yes? All of that is kinetic theory of matter. Now, relatively large amount of space between gas particles. Gas particles are in constant rapid motion, as are all particles. And they exert pressure on the walls of their container. This is not something we think about. Not really, okay? But gases do exert pressure on the walls of their container. Now, if we change pressure, temperature, and volume for a gas, talking about gases, we will affect physical characteristics. We can actually change the density of a gas by increasing the pressure. It's a thing, okay? So we're going to get into all of that. Now, we're going to look at Boyle's law first. This is our first gas law. We have 4 that we have to talk about. 4 gas laws, okay? The first is Boyle's law. If temperature is kept constant, this is Boyle's law. If temperature is kept constant, as the pressure of a gas increases, the volume will decrease. If temperature is kept constant, as pressure increases, volume decreases. Now, pressure and volume. According to this, pressure and volume have an inverse relationship, and they will show a curve when we graph them. And we're going to draw a graph in just a second. Okay? The equation for Boyle's law. This one, this is the gas at the beginning, and this is the gas at the end. Okay? It doesn't really matter which one you say is the beginning gas and which one you say is the end gas. It truly does not matter. What matters is that at a particular pressure, whatever the volume is, and you'll be told that, they must go together on the same side. Do you appreciate algebraically that that's how it would be? I mean, if these two got flipped, it didn't really matter. Okay? And what happens is, you're given 3 of these things, and you have to solve for what remains. Okay? Now, I want you to turn in your book to page 456. 4, 5, 6. Sketch this graph. Look at the graph on 456. Notice that it is comparing pressure and volume. If you won't. Is it not in that drawer? No. Yes. Hey, bring that back.
Okay.
Well, that's fine. Just be sure I get back today. Pressure and volume. Yes? Notice the curve. Do you see the curve? This is super important. Why is this super important? A lot of times when we see Boyle's law on the SOL test, it's a graph. They show you a graph, and they say, which gas law is this? Yeah? So, down here on the bottom of your slide, you're going to sketch this graph. Super easy. Volume. Pressure. Curve.
About as simple as it gets.
I mean, seriously. The assumption here is, of course, that this is set up like a regular graph, and it is. 0 is here, volume increases that way. 0 is here, pressure increases that way, yes? I mean, it's like a graph. You know, like graph. Yeah, okay.
So volume is
When pressure is at its highest, volume's at its lowest. You follow? When pressure is at its lowest, volume is at its highest. That's the inverse relationship. They're opposite each other.
Cool.
Yeah? Now, let's do Boyle's law. Let's do it.
We need sheet paper.
Nah.
Nah?
You can fit it on there.
Okay.
Yeah. Alright? Walk through this with me. The volume of the lungs is measured by the volume of air inhaled or exhaled. If the volume of the lungs is 2.4 liters during exhalation and the pressure is 101.7, these two go together. You with me? Does it matter if these two are together on the left or the right of the equation? It does not. But these two go together, okay? And the pressure during inhalation circulation is 101.01 kilopascals. What is the volume of the lungs? So you have these two that go together. You have this one that goes with, we don't know. That's what we're trying to find out. Capiche? These two go together, multiply, equals this one times, we don't know, liters. Question mark liters. Yes? Algebraically, what happens here? What do you do algebraically?
Divide 101.01 by the time.
Multiply 2.4 by 100.
Get this product.
Okay.
Yes? Or you can put it in the calculator, parentheses, 2.40 times 101, close parentheses, divide by 101.01, yes?
Yeah.
This is algebra 1. Yeah? So what is our answer? Do the math. What are you guys just sitting there? This is why I don't like to give you notes. Copy. Like, you're like sitting there. Like, where are you? What's happening? Today's Wednesday.
You sure?
At this time, 6 days from now, the SOL test will be over. So get here, be here between now and then. Quit being tortoises. Is that tortoise? I think it's tortoises. Snails, slugs.
I like to foresaw that stuff. I'm a morbid person.
What is it?
I got 2.4.
I got 2.42 liters.
Yeah.
Yeah? Guys, I'm not super stressed about sig figs at this point in the semester, because if you have a question about this on the SOL test, and you very well could, it's going to be a graph question, typically. In fact, I almost always see Boyle's and Charles' law, and we'll get to Charles in just a second, as graph questions on the SOL. Sometimes they want you to do the math. This is possible. Sometimes. But I typically see them as graph questions, okay? But if you have to do this math, the state of Virginia is very lenient in terms of sig figs. And I'll explain that to you more when we're actually in classic review time, okay? It'll blow your mind, some of the answers they will take, especially on one of those where you have to have a text box and you put the cursor in there and you type in your answer. They will take crazy answers, including ones that are rounded incorrectly. I don't know, whatever. All right, let's talk about Charles' law. Okay, Charles' law tells us that as the temperature of an enclosed gas increases, the volume also increases. What we're saying is that in this scenario, pressure is kept constant. Pressure on the system as a whole. Now, temperature up, volume up. I have two ways for you to remember this. Way number one. You could be not a tortoise and jot this in the margin if you choose. Way number one. You go get a batch of helium balloons for your BFF. It's the dead of winter. They blow them up to capacity in the food city. Then you take them outside where it's cold. What happens?
Pops.
Mm-mm.
No, they deflate.
They
The
droop.
volume increases.
They go like this. And they like start to sink.
Oh, it's
So instead of having straight strings, you have these bowed strings on all your balloons. And you're like, Food City helium is junk. But wait, because then you get to just junk where you're having your birthday party. And you walk in and the balloons are like, ah, and they begin to float again. Okay? Why is that? Because as temperature goes down, volume goes down. So the balloon was this big, and then you went outside and the temperature went down and the balloon went like this. Temperature down, volume down. Then you go back inside and the gas, the helium gas that's in that balloon gets warm. The temperature increases, the volume increases.
so if it was like, if they chilled Food City super cold, the air condition was blasting, and it was like 100 degrees
Outside?
outside, and you walked out with absolutely full to the brim helium balloons, they gosh darn diggity damn pop.
They could.
That's awesome. I want to do that. That'd be awesome.
Okay. Then way number 2.
Oh no, I'm good.
Way number 2. Okay? This is not something you should try at home,
Oh man.
but some of you may have already experienced this in your life because you are the age that you are, ill-developed frontal lobe, etc., etc. Okay? Pop bottle,
Oh.
water bottle, okay, emptied of liquid, and the cap put on tight, and then thrown into a fire.
Yes.
Oh yeah,
Yeah.
Yeah.
I burned myself.
Okay, now, before it actually melts, because you throw it in a fire, the plastic will melt, but before it actually melts, what is the potential danger?
That's the cat flying out.
The boom. Yes? Why is that? Because there's air in there. Is air gas?
Yeah.
Yes. You put it in the fire. Sometimes fires are hot, so the temperature increases. Okay. Temperature increases, so the volume of the gas that's in there must increase. It must increase, but it's got this container that's holding it in. So as the volume increases, the pressure inside actually increases, and it can compromise, and it can, okay? A way to try that and see the same thing that is not dangerous is to take a bottle that is empty of liquid, screw the cap on really tight, okay, there's nothing in there but air, and then stick it in your freezer. Couple, 2-3 hours later, you come back, and the bottle is like this. It's crunched, okay, which is cool, and you're like, oh, it shrunk, and then you set it on your counter, and as it warms back up, it's like pop, 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 and it comes back to normal size.
Is there
Okay.
any gas that isn't?
That would be a not dangerous way to see Charles' Law with a cheap plastic container. Yes? Now,
If I were to seal a propane tank and put it in the fire, that didn't have propane in it. Okay. Didn't have propane. Had like air. Would it go boom?
same thing. It's a
It
gas.
That's awesome.
Yeah.
I like life.
Okay, now, there is a direct relationship between temperature and volume. One goes up, the other goes up.
Yep.
One goes down, the other goes down. Yes? With Charles' Law, we always see a straight line. Oops, excuse me. When we graph it. Now,
We draw this.
we're drawing this one too. Turn to your textbook, 458. 458. 458. Figure 1410. Figure 1410. What's on the horizontal axis?
Temperature.
Vertical?
Volume.
The line is straight and it's up. Super easy.
Kaboom.
Boyle's curve, inverse relationship. Charles, straight line, direct relationship. Okay? Remember, inverse, one goes up, the other goes down. Direct, one goes up, the other goes up. Yes? All right. This is our equation for Charles' Law. Okay? Volume of the first gas divided by temperature of the first, or at the beginning, will be equal to volume at the end, or the second gas, divided by temperature at the end. Again, you'll always be given 3 parts of this equation. You solve for the fourth. Yes? All right, here's our example. Now, this is the example I just gave you, but with a balloon in the fridge or the freezer as opposed to a water bottle. Okay? The temperature inside my refrigerator is about 4 degrees Celsius. If I place a balloon in my fridge that initially has a temperature of 22 and a volume of 0.5, these two go together. Remember, it's V1 over T1. V1 over T1. Okay? What will be the volume of the balloon when it is fully cooled by my fridge? So this is T2. You're trying to find V2. Yes? show the algebra on your paper. I think you've got room on that little slide piece. Bless you. What do you get? 0.09090909. 0.09?
Dalton Wall, John Dalton. Is that his name? Yeah.
Now, I will tell you, when you have to do the math on the SOL for Boyles and Charles, what happens most of the time is my kids confuse which one is the multiply one and which one is the divide one. When V and T are together, I have always remembered it, even though I'm totally not a fan, but I have always remembered it like Virginia Tech. BT. You follow what I'm saying? The other one, there's no temperature involved. Okay? I don't know how you remember that, but it's PV equals PV. Remember, this is 1, this is 2. Okay? P times V, P times V. But VT goes above itself vertically. Okay? I don't know. It's just something you kind of have to crunch down and remember. I've tried a million ways to say, okay, Boyles, the name Boyles has the curve in the graph, and there's 2 curves in the name in the beginning of the B, and I've tried a million ways. You just have to, like, do it.
Have you looked it up in Google?
What? How to remember Boyles versus
I
Charles?
don't remember what it was. Let's do it.
Okay, now, here's what I want you to do. Separate paper or in your notes on the back. You want to do on the back of your pages, back of your slides that are copied for you, doesn't matter. I want you to do these problems right now. On page 456, you have an interpret the graph question. I want you to do parts A and B.
Well, look now.
Do you have this photocopied or no? Like, is this copied in your notes?
No.
Okay, I'm going to leave the screen up so you don't have to necessarily write them all down in advance. You can write one down and do it, write one down and do it.
Wait, interpret
Do you see on 456?
Yeah.
The interpret the graph section? So you're going to do A and B
Gotcha.
in there.
Oh, okay.
Do you see what I'm saying? When you're doing the interpret the graph, guys, you don't need to get your calculator out. I want you to read the graph.
So I just like write down the answer?
Yeah,
Okay.
you read the graph.
Cool down.
You guys are going to have to read graphs on the SOL test. Promise. Those questions are super hard because what you have to do is read the graph. That was sarcasm. Something that crosses my mind daily in this particular block. Shoop either is the only person in the room that gets my jokes,
I just laugh at everything.
or he's internally making fun of me. I can't decide.
No, it's not that.
You're a bully.
I just laugh at everything.
You're a bully.
My brother-in-law was my ecology professor my sophomore year of college, which was strange. I got a B in his class. I'm still sort of a little butthurt about that. But anyways, and I knew him because he was married to my sister and had been for quite some time by the time I had him in class. And he would tell jokes in class that nobody in the room got except me. And he would giggle. Like, he laughs at himself. So he goes, and you know he's like really cracked up when his shoulders move. But he's got a real dry sense of humor and really sharp. Really, like, you have to be smart to get his stuff. Which is maybe why
You got it.
some of the not super smart kids were like, is he having a seizure? What's wrong with him? Something's wrong. Why is his shoulder shaking like that? But I'd be cracking up. I think I should have gotten an A just for getting his jokes. But,
Yeah, that's.
yeah, whatever.
I
I got a
agree.
B. Still a thing. Every Christmas I see him and I go,
Should have got it. Should have got it.
really, dude? Really?
What did I do? Oh my gosh. I broke it.
If you're working on this at home, I'm going to turn the video off. When the video comes back on, we're going to pick back up. Okay, bye.